In this lesson, we will master the use of trigonometric identities, focusing on the pure mathematics 3 syllabus for the Cambridge 9709 examination. You will learn to manipulate fundamental Pythagorean identities, compound angle formulas, double angle formulas, and the harmonic form. These tools are critical because they allow us to simplify complex expressions and solve trigonometric equations that would otherwise be impossible to factorize. These topics appear frequently in the structured questions of Paper 3, often forming the basis of integration problems or complex number arguments. So achieving fluency here is essential for your A-star. Beyond the basic sine squared theta plus cosine squared theta equals 1, we derive identities for reciprocal functions. Dividing by cosine squared gives us secant squared theta equals 1 plus tangent squared theta. Dividing by sine squared gives us cosecant squared theta equals 1 plus cotangent squared theta. Let's look at an example. We need to solve 2 secant squared theta minus tangent theta equals 5 for theta between 0 and 180 degrees. First, we substitute our identity. By substituting 1 plus tangent squared theta for secant squared theta, we get a quadratic equation in terms of tangent. 2 times the quantity 1 plus tangent squared theta minus tangent theta equals 5. Expanding and rearranging gives 2 tangent squared theta minus tangent theta minus 3 equals 0. Factoring this quadratic, we get the factors 2 tangent theta minus 3 and tangent theta plus 1 equals 0. This gives us 2 possible values for tangent theta, 1.5 or -1. Finally, solving for theta within our range, we find that theta is approximately 56.3 degrees, or 135 degrees. We begin with the fundamental Pythagorean identities. You are already familiar with sine squared theta plus cosine squared theta equals 1. By dividing this base identity by cosine squared or sine squared, we derive identities for the reciprocal functions. First, secant squared theta is 1 plus tangent squared theta. Second, cosecant squared theta is 1 plus cotangent squared theta. In an exam, you use these to convert an equation containing both a squared term and a linear term into a single trigonometric ratio, creating a quadratic equation we can actually solve. Let's apply this to a specific problem. We want to solve 2 secant squared theta minus tangent theta equals 5 for theta between 0 and 180 degrees. Notice we have a mix of secant squared and tangent. We cannot solve this directly. Using our identity, we replace secant squared. Now, the entire equation is in terms of tangent. Let's expand and rearrange it into a standard quadratic form. Subtracting 5 from both sides gives us our quadratic. Now we factorize. This gives us 2 possible values for tangent theta. Tangent theta equals 1.5 or tangent theta equals -1. Finally, we calculate the angles. For tangent theta equals 1.5, the inverse tangent is approximately 56.3 degrees. For tangent theta equals -1, the angle is 135 degrees. Both are within our range. Next, we move to the compound angle formulas. These allow us to expand trigonometric functions when the argument is a sum or a difference of 2 angles. The sine of a plus or minus b follows the pattern sine, cosine, then cosine, sine. Note that the sign remains the same. The cosine expansion is different. It groups the cosines together and the sines together, but the sign is reversed. A plus in the bracket means a minus in the expansion. The tangent formula is a fraction, where the numerator keeps the sign and the denominator reverses it. In Cambridge 9709 exams, these are vital for show that questions, where you must manipulate one side of an equation to match the other. Understanding the structure of these formulas helps you spot when an expression can be condensed back into a single term. Let's simplify the expression cosine of x minus 30 degrees minus 3 sine of x minus 60 degrees. We expand the first term using the cosine difference formula. Cosine x cosine 30 plus sine x sine 30. substituting the exact values for cosine 30 and sine 30. Now for the second term, expanding the sign difference. 3 times sine x cosine 60 minus cosine x sine 60, which is 3 times 1/2 sine x minus root 3 over 2 cosine x. This gives 3 over 2 sine x minus 3 root 3 over 2 cosine x. Now we subtract term 2 from term 1. We subtract the second result from the first result. Group the like terms. We have 2 terms with cosine x and 2 with sine x. Simplifying the coefficients gives us 2 root 3 cosine x minus sine x. This reduced form is much easier to work with if we were asked to solve an equation or integrate. Double angle formulas are a specific case of the compound angle formulas where we set a equal to b. They are essential for reducing the degree of an expression or changing the frequency of a trigonometric function. For sine, the expansion is straightforward. 2 sine a cosine a. Cosine 2a is unique because it has 3 forms. The primary form is cosine squared a minus sine squared a. By using the Pythagorean identity, we can also write it as 2 cosine squared a minus 1, or 1 minus 2 sine squared a. In exams, choose the version that matches the other terms in your equation to allow for easy factorization. Visually, look at the difference between cosine x and cosine 2x. Doubling the angle doubles the frequency. While cosine x has a period of 2 pi, cosine 2x completes a full cycle in just pi radians. This frequency doubling is why we need these identities to solve equations where arguments differ. The harmonic form is one of the most powerful techniques in the pure mathematics 3 syllabus. It allows us to combine a linear combination of sine and cosine into a single phase-shifted wave. This is essential for finding the maximum or minimum values of a function and for solving equations where the variable appears in both sine and cosine terms. We can express any combination of the form a sine theta plus b cosine theta as r sine of theta plus alpha. The value r represents the amplitude of the resulting wave and is calculated as the square root of a squared plus b squared. The phase shift alpha is found using the inverse tangent of the coefficients. Be careful to use the correct signs of a and b to determine which quadrant alpha lies in. Using this form transforms an equation with 2 different trigonometric ratios into an equation with just one, which we can then solve using standard inverse trigonometric methods. Let's solve 3 cosine theta plus 2 sine theta equals 1 for theta between 0 and 360 degrees. We first express the left side in the form r cosine of theta minus alpha. Here, a is 3 and b is 2, so r is the square root of 13. The phase shift alpha is the inverse tangent of 2 divided by 3, which is approximately 33.69 degrees. Now we solve the simplified equation. Divide by root 13. Taking the inverse cosine gives us 2 possible values. Remember that cosine is positive in the first and fourth quadrants. We add the shift to find theta. Our 2 solutions within the requested range are 107.6 degrees and 319.8 degrees. On the graph, you can see the wave reaches a maximum height of root 13. The line y equals 1 intersects the curve at our 2 calculated points. Now, let's look at a question typical of a Cambridge 9709 past paper. Consider the equation 3 sine 2 theta equals 2 cosine theta. We are asked to show it can be rearranged for solving. First, we apply the double angle formula. For sine 2 theta is 2 sine theta cosine theta. This is the crucial step to make the arguments the same. Next, we move all terms to one side. Never divide by cosine theta, as you might lose valid solutions where cosine theta equals 0. By factorizing out 2 cosine theta, we achieve the required form. To solve for theta between 0 and pi, we set each factor to 0. From cosine theta equals 0, theta is pi over 2 within our range. From sine theta equals 1/3, the principal value is 0.340 radians. For sine, The second solution is pi minus the principal value, which is 2.80 radians. These three solutions, 0.340, pi over 2, and 2.80 are our final answers. Let's discuss common pitfalls to avoid in your examination. The most frequent error is dividing both sides of an equation by a function like sine or cosine. As we saw in the previous example, this removes potential solutions. Always move terms to one side and factorize instead. Students often find the principal value but forget to search for all solutions within the given interval. Check if the question is in degrees or radians, and always use the quadrant rule or the graph to find every intersection point. Specifically with the cosine expansion. Remember, cosine is antisocial. A plus in the bracket means a minus in the expansion. Mixing these up will lead to an incorrect final simplified form, costing you accuracy marks. Squaring can introduce extraneous solutions that don't actually satisfy the original equation. It is much safer to use the Pythagorean identities or the harmonic form to keep the equation linear in terms of the function. When sitting your pure mathematics 1 or 3 papers, keep these examiner insights in mind to maximize your marks. Examiners award method marks for the correct application of an identity even if your final answer is wrong. Always clearly state which identity you are using. For example, write down using sine 2 theta equals 2 sine theta cosine theta before substituting. Unless specified otherwise, use exact values like root 3 over 2 during intermediate steps. Rounding too early in a long trigonometric derivation will lead to rounding errors that could lose you the final accuracy mark. In show that questions, the destination is given. If you get stuck, look at the target expression. If it contains only tangents, that is a massive hint to use identities that eliminate sine and cosine as early as possible. Check your calculator mode immediately. A common reason for losing all accuracy marks in a question is providing answers in degrees when the range was specified in radians. It is time to test your understanding. Please pause the video and attempt these 3 questions before we go through the solutions. Question 1 is an easy application of the double angle formula. Question 2 requires a Pythagorean substitution and solving a quadratic. Question 3 covers the harmonic form and its application to finding maximum values. Pause the video now. Let's look at the solution for question 1. This matches the form of the sine double angle identity 2 sine A cosine A. By identifying A as 15 degrees, we condense this to sine of 30 degrees. This gives us the exact value of 0.5. For question 2, we solve the quadratic. We replace secant squared with 1 plus tangent squared. Rearranging gives us a factorable quadratic. This means tangent of x equals 1/3 or 1. Taking the inverse tangent gives our 2 solutions. For question 3, the harmonic form. R is the square root of 5 squared plus 12 squared, which is exactly 13. Alpha is the inverse tangent of 12 divided by 5. The expression is 13 sine of theta plus 67.4 degrees. Since the maximum value of a sine wave is 1, the maximum value of this expression is simply r, which is 13. To summarize today's lesson on trigonometric identities for the Cambridge 9709 syllabus. First, always use the Pythagorean identities, like secant squared equals 1 plus tangent squared, to transform equations with mixed terms into a single trigonometric ratio. Second, remember that compound and double angle formulas are your primary tools for simplifying expressions where the frequencies or arguments of the functions do not match. Third, the harmonic form is the most efficient way to solve equations involving a combination of sine and cosine, and it immediately reveals the maximum and minimum values of the function. Fourth, in terms of exam technique, never divide through by a trigonometric function. Always move all terms to one side and factorize to ensure you don't lose valid solutions. Finally, consistently verify the required range and ensure your calculator is in the correct mode, radians or degrees, before you begin your final calculations.